Good day everyone, welcome to my channel. Today we are looking at linear functions and analytical geometry. Before we start with this concept, it's very important to understand that when you talk about linear functions, we are talking about lines or straight lines. Okay, and then basically or rather essentially we talk about analytical geometry in a sense that we look at how straight lines apply on a Cartesian plane. So we're gonna use the regular coordinate system to be able to understand how this application works. Suppose, for instance, you have a Cartesian plane. Okay, I'm gonna use this color. Suppose you have a Cartesian plane. I'm going to have to devise a Cartesian plane. Okay. So now it's very important for us to understand what we mean by a Cartesian plane. So I'm going to have our Cartesian plane. So we have our Cartesian plane. Now it's very important to identify the Cartesian plane as our x and y intercepts. Rather, should I say rather, this is now y, this is now line y, this is our y-axis, and we have our x-axis. And now we have our first quadrant in the space, and we have our second quadrant, our third quadrant, and our fourth quadrant. So there are 4 quadrants on our Cartesian plane. Now, on our Cartesian plane, again, very important to understand that when you look at the Cartesian plane, x and y are positive in the first quadrant. In the second quadrant, x is negative, so we have x as being negative, and then y is positive. Then our second quadrant. In our third quadrant, we have x being negative and y is also negative. And then lastly, x is positive and y is negative. That's key in understanding how these coordinate systems work. And one key aspect that I'd like to look at also is to know that this is our origin. So we have x is where x and y intersect. So rather basically, that's what you call the origin. Okay, we call this mathematically the origin. Essentially what this means is that x is at 0 and y is also at 0 at that point, this point where they intersect. Okay, now the Cartesian plane is divided into 4 quadrants by a pair of number lines that we call the x-axis and the y-axis. The 2 axes intersect at right angles at the origin. Rene Descartes, 1596 to 1650, described the idea of using ordered pairs to represent points in the plane in his book, La Geometria, which was published in 1637. Each point on the Cartesian plane has an ordered pair of x and y. The first number in the pair is the x-coordinate, and the second number in the pair is the y-coordinate. So which means it's very important that one needs to understand that when you deal with Cartesian planes, you have to start with x first and then y. Okay? If a graph shows a relationship between 2 variables by means of a straight line, we then call the relationship a linear function. Now, linear functions, I will just highlight this shortly. You will learn more about these in the next chapters. Now, I would like to point a couple of things with regards to the Cartesian plane. I have to revert back to my first starting part. Okay, let's go back. I'm going to have to amplify this Cartesian plane so that we are on par with the principle itself of how the Cartesian plane works. Okay, so suppose now we still have our Cartesian plane. This is our Cartesian plane. I have to measure this. This line is a line of 120 centimeters. So basically, no, 120 millimeters. So which is 12 centimeters. So I'm going to extend this. So just basically get 60 millimeters here. Okay. Now, and then draw a horizontal line, so x-axis in this case. I'm just going to actually just draw it right V. Okay, I have to plot it. Let's just have it here. Stop here. Okay, this is our Cartesian plane. Now, there are very important aspects to look at when you look at this Cartesian plane. So, I'm going to use an arrow to indicate that these lines can continue to infinity. So, we have our x-axis and we have our y-axis on either side. So, x and y. So, essentially what this means, it means that this Cartesian plane, like I've indicated early on, we have our first quadrant, second, third, and fourth quadrant. Now, I need to graduate this Cartesian plane further by giving markings on this. So let's go ahead and mark. I'm going to actually mark this part here. Let me start off with the x-axis. So I have 1, 2, 2, 3, 4, 5, 6 units. 1, 2, 3, 4, 5, 6 units. So you have 6 units on either side. I'm going to do the same on this side here as well. So 1, 2, 3, 4, 5, 6, 6, 1, 2, 3, 4, 5. Okay, we are safe. Now, I need to indicate a couple of things here. So we know from the origin, from here, starting from the origin, this point here, x is 0 and y is also 0. So that's our origin. So we have 1, 2, 2, 3, 4, 5, 6, and then here we have -1, -2, -3, -4, -5, -6. Similarly, we have -1, -2, -3, -4, -5, -6. We have positive values here: 1, 2, 3, 4, 5. Okay, now this is how the Cartesian plane works. Now, when you look at all of these values here, starting from the origin, moving to the right, from the origin moving to the right, we have all positive values. Like I said earlier on, in the first quadrant, x is positive, so we have x as being positive, and notice that y in this space here is also positive. So all these values, starting from the origin going to infinity, are positive, and all these values starting from 0 going to the right are positive. So x and y are positive in the first quadrant. So we have our first quadrant, x and y are positive. So in the second quadrant, let's look at the x variables, or rather values. All the x values are negative in this case. So x is negative, and then all these are the values I'm talking about, starting from the origin, starting from here, going that way. The values of x are negative, and all the values of y are positive. So y is positive. Let's move on to look at the other values here, the third quadrant. So we have our third quadrant now. So x, in this case, let's look at x. X is still negative, so all these values going that way are negative. So in this quadrant, all the x values are negative. And then let's look at all the values for y. They are also negative. So both x and y are negative in the third quadrant. Let's look at the fourth quadrant. Now these values of x are positive, so x is positive in this quadrant, and then y is negative in the third quadrant, in the fourth quadrant. So that's essentially what we mean by negative, positive of quadrants, or rather coordinates in this case. So let's look at how this system works in terms of plotting the values. Okay, I'm gonna now go back. Okay, it's very important that I go back. I need those values. Now, okay, now to be able to understand this application, so we need to plot the points P, which is -1, and positive, or rather -2. Okay, so P is at -1, so we have P here at -1 and -2. So -1, -2 are here, the intercept here. Okay, so that is point P. Now let's look at Q. Q is -1 and 0. So -1 and 0 is the intercept there. So that's their intercept. So you have Q here. And then R is positive 2, and y in this case is 0. So y is 0, and then x is 2. So r is this point here. So we have r there on the line where 2 is. So s is the origin. Our origin now in this case is 0, and y is also 0. So we have this intercept here where they both intercept. So we have point S. T is at x is positive 1, and then y is positive 2. So the intercept so that's where t is. So the t intercept is there. So x is 1 and y is 2. And then u is negative 1, and then our x is our y is 3 in this case, so the intercept right there. So this is our u. V, x is negative 2, and then our y is 3. So the intercept right there. So we have v. Okay. So now this looks like more like a rough application, but I like to indicate it by amplifying, even providing a much better, clearer version of this. Okay, so very important to note that whenever you work with Cartesian planes at the first instance, we are gonna need to be very messy. It sounds like it's prescriptive, so it's not a problem to be messy. So let's actually now devise this now in a proper mathematical format. So now to do that, I suppose now we draw our Cartesian plane now in a proper fashion. So now in this case, we're gonna have our proper Cartesian plane. So a line there, second line, horizontal line, runs across like that. So this time I'm not gonna take it in units of 1. I'll take them in 2s now, so that it's clearer. 1, 2, 3, 4. So it's very important that our second application is much clearer and concise. 1, 2, 3, 4. So we still have our x-axis. Okay, so we need to devise our y-axis as well. So our y-axis in this case, let's devise it right here. So our y, we have 1, 2, 3. Okay, 1, 2, 1, 2, 3. So this is our y-axis and this is our x-axis. Okay, now when we look at these two axes, so we know that this is positive. These are positive values ranging from the origin going to the right, and these are negative values ranging from the origin going to the left. Okay, now these are negative values starting from the region going to the bottom, or sub-zero. So these are our negative values. And these are all positive values, and so forth. Okay, so we have our x axis, and now we have our y axis. Now, what I'd like to look at now in this case, suppose now we want to find the line that runs from this point. In fact, before we start with lines, so let's look at the associated pairs of these, like we did. Likewise, we did with the first example before we became messy. With this exercise, so we have p at -1 and negative x being -1, and then y is being -2. So they intersect right here. -1, -2. So that's our p. So you have to be as accurate as possible. So let's look at the next point. Q now is -1 by 0. So this is our point. So this is Q. Okay, now it becomes clear. And then R is 2 by 0. So that's the point there. We have R there. And then S is 0 by 0. So this is our origin. It's actually at the origin there. So we have S. And then T is +1 by 2. So that's our point. So we have T. U is -1 by 3. So we have U right here. And then V is -2 by 3. So this is our V. Okay, so those are our points on our coordinate system. So now to find the ordered pairs associated with each of the points given below, for instance, we find the distances between A and D. So we need to find the distances between A and D. Let me indicate this. Between A find the distance between A and D. Now to find the distance between A and D, we need to use the distance formula. Now the distance formula applies like this. So this is our distance formula. Let me write it somewhere. Yeah, can we get a space? So our distance formula, say D is equals to the square root of x2 minus x1 raised to the second power plus y2 minus y1 raised to the second power. D is equals to, let's substitute. Now let's start with x. So now we need to look for D, A. In this case, first the distance. In actual fact, we look at the actual point where A is. Looks like we didn't get A. The question asks us to look for A. Okay, suppose it looks like there's a second example that we're gonna be looking at shortly. But suppose that we need to find the distance between say V and R. So in this case, instead of finding between A and D, oh no, let me do this. Okay, now we're going to find the distance between V and R. So our distance between V and R. So our V in this case, we know that our coordinates for V are, first starting with X, remember? So we have -2 by, or Y in this case is positive. Okay, that's for V, this point V, this point here. Okay, and then we look for point R. R is, X is positive 2, and then Y is just simply 0. This is the point here. Okay, so now we need to substitute that into our equation. So it would follow like this. So let's substitute X. Can take any value between R and V. So I'll just simply start with V. So we have -2 minus, okay, R in this case, X is 2 raised to the second power plus, open bracket, Y in this case for V is 3 minus, Y for R is 0 raised to the second power. D, still want to find the distance. Remember, we're squaring everything. So let's calculate. -2 minus 2 gives us -4 raised to the second power plus 3 minus 0 is just simply 3 raised to the second power. D is equals to, remember now, 4 times 4 gives us 16. Remember, we're still squaring this. So we get 16 plus 3 times 3 gives us 9. So D is equals to 25. When you, then now these are in unit form. So in other words, the distance from V to R, this distance here, this distance from V to R, is 25 units. Okay, that's what it means essentially. So let's find, for instance, the distance now from let's find the distance from P to Q, from P to Q. So we're going to say P, okay, P, the coordinates are, I was starting with X, so it's -1, and then Y in this case is -2, and then Q, X is -1, and then Y in this case just simply 0, because this is the point, these are the 2 points I'm talking about. X is -1 for Q, and then Y is just simply 0, and then for P, X is -1, and then Y is -2. So now to find the distance using this distance formula, I'm just gonna simply say D is equals to, using the distance formula, goes like this: x2 minus x1 raised to the second power plus y2 minus y1 raised to the second power. Distance, D for distance, square root. So our x, you can take any variable that you like to take. In this case, You can start with P or Q, either way. Doesn't really matter. It will still yield the same answer. So D, we have D. It's very important that we put this in the bracket. So let's start with P this time. So P, in this case, we have -1 minus, remember now, this Q here, our Q, X for Q is -1. So we close this in a bracket, raised to the second power, plus Y is -2 minus 0 raised to the second power. D is our difference, our distance rather. So we now have -1 minus, okay, let's just simply write it, -1, negative times negative gives us +1 raised to the second power, plus 2 minus 0, minus -2 minus 0 gives us -2. Okay, so the distance is equals to square root of, so -1 plus 1 gives us 0. Okay, just simply raise to the second power and we're gonna get 0. So we have -2 multiplied by -2, we get +4. So distance is equals to 4. Now when you square that 4, the distance now becomes 2 units. Okay, so in other words, distance from P to Q is 2 units. This distance there. Okay, and it looks like it's just a vertical line. Now let's look at another last example. Okay, I wonder which area to use now. Okay, let me try and use the space. Okay, check. Use the space. Let me clear here. Clear here. I think it's clear here as well. Right. Now, to look at the distance, from S to T, this distance here, use this pen is fine. This distance here, from S to T. So now we are looking at a distance from S to T. So what we need to do, using the same application of the distance formula, we're going to say D is equals to the square root of x2 minus x1 squared plus y2 minus y1 squared. D is equals to, by substitution, we're going to now start looking at the variables. Now S, let's start looking at the variables of the coordinates of S. So X is 0 and Y is also 0. T t now, our x is 1, and then our y coordinate is 2. Okay, so now let's substitute. So at s, x is 0 minus our x for t is 1 plus our y for s is 0. Oops, sorry. Minus our y for t is 2. Okay, so distance is equals to square root. Okay, 0 minus 1 gives us negative 1 raised to the second power plus 0 minus 2 gives us negative 2 raised to the second power. Distance is equals to, okay, 1 times 1 gives us 1 plus 2 times 2 gives us 4. Distance is equals to, so here we have square root of 5. So if you square 5, we get, let's see on the calculator, what do we get? When you square 5, we get 2 comma 2,4. It's now rounding off to 2 decimal places, units. And then that for today brings us to the end of our introduction to linear functions and analytical geometry. I'm going to post most of these videos in the next coming lessons. So this was just basically an introductory part to linear functions. We're going to look at more of these examples in the next coming videos. Please like, share, and subscribe to this channel so I can create more of these educational videos and content. Thank you. Goodbye.